Well, welcome everyone. Thanks for your dedication and giving up your precious time on the weekend and the energy required to do that as well. So we've only got a relatively short time to talk about quite a big topic. So I don't pretend to cover all the things that I could talk about around algebraic thinking, but I'm just going to pick out a few things that I think are really important. And normally what we would have if we were working through something as rich as this as a topic would be a whole day of PD, but we don't have that privilege. So we're just going to sort of give you the Vince Wright take on algebraic thinking. It was the topic of my master's thesis a long time ago, and I have maintained a research interest in algebraic thinking since then, done other things as well, of course. The little scenes you can see there are from some classes in Melbourne where I worked for 6 years, not in those classes at a university, but we did a lot of modelling in schools. So you get a sort of flavour of what this is likely to look like from those pictures. Okay, I'm going to admit, oops, hello, I'm sorry, we've got something else in the road here. We'll just make sure that there's nobody waiting. Okay, so what I've got here is the refreshed curriculum, the latest edition in May 2023, and I've just chosen the do part of the curriculum around algebra. And now there are other things, of course. There's the big ideas, understand, and there's also the do's, which are more about sort of mathematical practices and ways of working. So I've just chosen to concentrate on the know part of the algebra strand. And what I want to do really is to just highlight the way in which it's structured, and it's very much following the way the 2006-7, depending which edition you want to look at, curriculum has. And it's so basically I'm just going to try and show you what are kind of the bits that fit in this this algebra strand. And you'll see if I color code this a little bit, and it actually works. It actually animates. Come on, there we go. You'll see there's a bunch of progress outcomes that are devoted to properties of numbers when they're being operated on. That's the best way I can think of to describe it. So you see there things like the distributive property, the commutative property. So in each of the years that we have progress outcomes for, and we're getting some in between as well, you'll see that. You'll see some stuff about number properties and under the operations. So it's a nice way to kind of think about it. That's that main block there. We'll talk about some ways that you can develop these ideas with students, of course, as we go along. And then you will also see a block that seems to be talking about patterns and relationships. And you'll see this is year 6. So we have a kind of mixture in year 6 where we have what we would call sequential pattern, which is, if you can think of a sequential pattern as a one after the other pattern. So a sequence is a sort of repeated thing. And growing patterns tend to be a little bit different in the sense that that we're looking at a relationship between two features in the growing pattern, and we'll certainly show you some of that. And it's suggesting that we might use tables and number planes, XY graphs is the terminology they're using, to represent those patterns. And then there's a little bit down the bottom, which is around computational thinking, which has its roots in computer science, but other areas as well. But that's where its real home is. And it talks a lot about algorithms, and algorithms are just a set of procedures to achieve some sort of goal. So it's really important to distinguish an algorithm from kind of a problem. An algorithm is just a set of steps you follow. Now, that kind of structure actually is applied right across the different year groups, at least at primary school anyway. And you can see if we look at year 3, we can see a similar sort of pattern. We've got the number properties under the operations we're talking about, and you see equality and inequality coming in as early as year 3. And you also see that the patterns, the yellow outcomes are there as well. We're tending to think more about a sequence at year 3. And the students identifying what we might call the unit of repeat. In other words, the block of objects that are repeated as this pattern progresses. And once again, we've got computational thinking and the word algorithm coming in. And if we go to year 8, we've got a similar kind of pattern. We have a little bit of a crossover when we start thinking about solving equations, because we're actually solving equations often in the service of finding some value in a relationship. So they kind of overlap there, and certainly the idea of a variable is certainly tied in to the idea of the operations, as we'll see. We'll look at some examples again. So the same kind of pattern is through, and that's a nice way of kind of thinking about, if you like, the 3 things we really have to do. That's not to say that they are always treated separately, but it's nice to think about that structure as a way of organizing our thoughts about what we're trying to do. Okay, let's show you some examples of, and so I'm just taking an example that I used at a year 4 class a couple of weeks ago. So let's think about how we might develop understanding of different sets of numbers under the operations. So in Australia, where I worked for a number of years, they actually had some elements of proof way back in fairly early in primary school. So here's an example of that. So I asked the students if they could tell me if there was something in common with these numbers. And some of them seemed to know that they were called odd numbers. I was very keen that they had some kind of spatial representation of that, because I wanted them to get into generalizing something about odd and even numbers. And so if it's going to work, there we go. So we talked about, I wonder why they were called odd numbers. And this kind of graphic representation is really close to the mathematical definition of what an odd number is. So it's a multiple of 2 plus or minus 1, whichever way you want to go. But this representation, as you can see, is kind of going, okay, well, we could think of 1 as just sort of itself, and we could think of 3 as being a pair with 1 extra, and 5 as being 2 pairs with 1 extra, and 7 as 3 pairs, etc. And so they seem to be able to consider the idea of odd as being like, you can pair, like if we had a class of kids and there were 7 of them, and we could pair them up, but there'd be 1 person, there'd be an odd person out. So that seemed to resonate with them quite nicely. I'll just admit Joe. Here we go. Okay. And we did something similar with trying to represent the even numbers as multiples of 2. Need to be a bit careful because we're talking about using whole numbers, so 0 is usually classified as an even number. And so you got that idea. Yes, okay, we've got that idea. That's really good. So here's some numbers. Now, are they even or odd? And of course, I'd been a bit strategic about the choice of number size, because what I wanted them to do was to start thinking about divisibility by 2, and then thinking about, well, would there be that odd one left over if we made pairs? And so I pushed the numbers out just far enough that they couldn't just obviously visualize that. They had to think about it really hard, and they got quite nice at being able to classify them. And then we talked about, well, is there a way to tell whether straight away, no matter how big the number is? And they started talking about the ones digit and whether the ones digit was even or odd as being a way to tell. So that was nice. And then I wanted them to start doing some thinking about what happens when you add and subtract, mainly add at the start anyway. That's far enough in one lesson. So we talked about specific examples. So what actually happened when you added 2 odd numbers? Now, here was an example. 3 plus 5 equals 8. Now, why is it that when you when you added two odd numbers together, you got an even number. And of course, geometrically, they were saying things like, well, actually, if you take that odd one at the top, you can probably see the cursor, and drop that in there and put these on top, then you end up with an even number. So these two, if you like, the odd elements give you another even number and another multiple of 2, and you're away. It's always going to be the case. So we gave them some time to kind of investigate, was that always true? Try some different odd numbers and think about why that is. And what happens when you add two even numbers together, or you add an odd and an even number? And students certainly at year 3 and 4 are quite capable of doing that kind of thing. You can see how we've got elements of generalization. Now that word's shot through in the do's of the curriculum. So generalization is recognition that something is the same, it's consistent, it's always happening. We might be interested, as we are here, in why that happens, which we would describe as the structure of what we're doing. So generalization involves noticing there's a pattern, but also considering the way it's structured. With another class, we talked a little bit about odd and even numbers at the start, and I just thought, well, okay, maybe we'll just try a different angle here. And so we gave them a sequential pattern, and then we attach the ordinal numbers to those. So if you like, the yellow triangle is the first one, blue square is the second one, etc. And then ask them to tell us about what was the same about all the odd number ones. What shape was always under the odd numbers, and what shape was always under the even numbers, and they could pick that pretty well. Of course, the obvious thing to do would be to say something to them like, well, what shape do you think the 13th one would be, for example? And so they're having to extend the pattern beyond what they can see and start reasoning about how you would think about 13 and how that would help you figure out which shape was there. So there's some really nice tie-ups to sequential pattern. I think it's vitally important that sequential pattern is connected to the ordinal numbers, because for two reasons. One, that gives you the function, and a function is kind of a one-by-one mapping. Not entirely correct, but close. And so that's what that does. We're mapping the ordinal numbers to the shapes. And the other thing, it gives us a vehicle for getting the students to predict ahead, and ultimately improves their connection between addition, repeated addition, and multiplication, and sometimes division, actually. So I'm not going to spend time on this. This is just to show you that these patterns can become very complicated. The more variables you throw in there, the more complicated the patterns. It's not just about the size of the element that repeats, or the unit that repeats. It's about what variables are going on as well. So that's a more complicated example, where you've got shape changing in a different sequence to color. So colors changing in patterns of 2, and shape is changing in patterns of 3. So predicting what the 99th one is going to be is a bit of a challenge. Okay. Go. It's just sometimes it goes and sometimes it doesn't. Okay. I'm just going to show you something completely different, actually, that ties in with odd and even numbers. And I think it's really nice because it moves beyond what we traditionally think of as those kind of pattern activities, and yet it involves the students applying odd and even numbers. And I'd love to claim this as my own, but unfortunately I can't. I'm going to show you, I'm going to just stop sharing, and then I'm going to show you what the set of cards look like. Now, you can see the claim there that I'm having trouble removing things. Here we go. If the cards are just thrown down on the ground, if there are two odd numbers showing, then you don't need to add them. You can just know that the sum is always 28. Now, I'll show you what we mean by that. So just remember, if two odd numbers are showing, the sum is always 28. So I'll stop sharing, and then I'll just show you what The cards look like. And I'm just going to go here. Okay, so this is how hard it was. Oh, very difficult thing to do. So I'd made up a set of cards, and this is what they look like. So there's one on one side, two on the other, three on one side, four on the other, and it just keeps on going. 5, 6. When I can undo it, we've got 7 and 8, and we've got 9 and 10. Okay, then I can undo. So we're basically saying, what was the idea that Miss Poihapi had? Well, she had the idea that if it didn't matter how they were thrown down, but if there were two odd numbers showing, let's imagine, here we go, we had these two odd numbers showing, and you added up the cards, they would always come to 28. And that's a lovely example of how you might get students to generalize, to look at a claim and generalize whether it's true or not and why it might be true. So they might see a pattern, they try lots of examples, but why is it that if two odd numbers are showing, the answer is 28? I suppose we better check that it is. Here's an example. So we add those up. What have we got? We've got 18 here. 24, 28 seems to work. So the students did a lot of examples and were pretty happy that Mrs. Poihapi's idea actually worked all the time. And the big challenge then is, can you think about the structure of the problem and why that actually happens? And we did have students doing things like, well, I just kind of imagined they were all even. So if I made them all even and added them up, they came to 30. Now, what happened when you turned over any two cards to make them odd? Say I did that, then I took 2 off, and that explained why the answer was always 28. So what you've got there is, I mean, it comes from a project where they looked at developing proof with quite young students, and the activity, I think, is from Jill Brown, a colleague of mine in Melbourne. I think it's lovely because what it's expecting kids to do is not just notice a pattern, it's actually getting them to think about the structure and why that pattern occurs. And that's something we need to be doing all the time. Okay, so I'm going to go back to the PowerPoint. See what could possibly go wrong. Just about everything, probably. There we go. And we're off in a different place. It's usually the way. Okay. So here we go. So so those kinds of things are interesting in the sense that they can tie into spatial pattern, in the sense you've given the students a kind of visual of what an odd and even number looks like. But then we've pushed that beyond just a spatial image, and we're thinking about what's happening with a set of numbers. The idea of how you develop generalization of number properties that's been explored by lots of people far wiser than me, and there are a lot of different approaches that people have tried in the research, and this is one that two academics thought about, and you would have seen examples possibly like this where we have the unknown in different places. And a lot of people have attributed students' difficulties to understanding equality. I don't think that's the only thing in play in these examples, but the idea here is that you could actually figure out what goes in the box without having to actually do the calculation. So if you're reasoning with calculation, you might do something to the top one, like go 7 plus 10 is 17, and then find 8 plus what is 17. So that would be a calculation approach. If you're thinking, well, I would say without closure, which is out having to close off the calculation and thinking about number properties, then you might notice, and some students do, of course, that the 8 is 1 more than the 7. So this number here in the blue box here must be 1 less than the 10. And the people that developed that idea, it's not just theirs, but they've certainly done some really nice research with Max Stevens, Professor Fuji, I don't know his first name, from obviously from Japan. And so that's their idea of presenting these kinds of problems to students and seeing if they can develop what they're calling relational thinking. It's very easy to get confused with. Marla would be going, I'm thinking of relational thinking and Richard Skemp, but they used the same term for something different. And what they're asking students to do is reason across the equality, and the unknown is in different places. And the bottom one's a little more challenging because you've got the number property of the commutative property kind of happening there. It might be easier if the 3 was on the right-hand side, might not. But I mean, there's a tripling and thirding going on there. So 3 is a third of 12. So this number in here, is a quarter of 12. So this number in here should be 16 because this one has to be 4 times bigger. So multiplicative thinking, it's a little bit harder. I'll just say that again more slowly. So relational thinking would say, oh, okay, the 3 is 1/4 of 12. So this number in the box would have to be 4 times the 4 to balance it. So it can get quite complicated, especially if you're dealing with proportions and things like that. Here's something that we've borrowed. We'd like to borrow lots of things. This comes from Deborah Shifter's work in the United States. And this is, I think I'll put a link at the top there. You can just search for this if you like. There's a couple of units called What's Going On. And we start with this kind of idea of saying, okay, well, I just want you to fill in the box, right? So what's the answer to this? Now, we know that students might actually have to calculate 36 times 5 rather than recognize the commutative property that they'll have the same answer. But basically what we do when it works, when it goes, is when it works. Oh, there we go. I don't know why it's taking so long. It's just interacting. So we basically generate 4 examples that are the same in some kind of way. And then invite the students to make a claim about why they are the same in some kind of way. And if you follow the process that Shifter and colleagues do, it's quite different than what we would normally do. What we would normally do is start with some sort of materials and then generate the equations from them, but they start the other way. So they start with equations and expect students to notice pattern in those equations. So something the same going on. But then the really nice thing about their approach is they invite the students to make a claim about what's going on. And then they kind of fold back into materials and say, well, okay, your job now is, can you show in some kind of way what's going on there? So they're really getting at structure. So they'll go back to physical materials or diagrams, maybe even stories about that represent the equations that they've just seen. And then they're asking the students to construct an argument which would convince somebody else that this property always holds. So the last one was a commutative property of multiplication, of course, but if you go to those units called What's Going On, you'll see there's some really nice examples related to fractions, for example. So it's a really nice model, and it's different than what we would normally do because it starts with the equations, folds back to materials, inviting them to try and represent what's going on, and then ends with them constructing some sort of sensible argument for somebody else to convince somebody else about why it works. And again, I'm trying to get this to go. Okay, here we go. Here's another approach that I dearly love. And will it allow me to scribble things? Oh, yes, it's always good when you can scribble. Okay. So you ready, folks? Here we go. Just imagine you're in my class, you poor souls. Okay. So what I want you to do when it goes, I want you to think of a number that's a whole number less than 10. So let's not make it too complicated. 7.85 is off the table. So you're thinking of a whole number less than 10. So just write your whole number down, or hold it in your head if you can. And I want you to double your number. So take the answer to that, your number doubled, and add on 6. Now divide the answer to that by 2, halve it. Now I want you to take away the number you first thought of.
14.
And what's your number? So let's just see if I started with, I think of a whole number, say I start with 3, I double my number, I get 6, I add on 6, I get 12, I halve that, I get 6, take away the number I first thought of, which was 3, and I end up with 3. And the interesting thing is everybody ends up with 3. Well, if they get their calculations right, they do. And the interesting thing you challenge students to do is to say, well, okay, everyone's got 3. Now, I don't think you were cheating. I don't think you're looking at the person next to you. You were actually starting with different numbers and getting the same answer. Now, why would that happen? And it's fascinating to work with students on this and see them trying to explain why that happens. I like to use if I can draw it, I like to use a kind of what's called a cups and counters analog here, which is basically letting a cup represent whatever number you've chosen at the start. And counters are ones in this, okay? So I'm just going to draw circles instead of cups just to save some time. So I double my number. What does that look like? Oh, it looks like that. Now, algebraically, that's 2n, of course. And when I add on 6, what do? I add on 6. I've got 2n plus 6. I divide it in 2. Now I end up with that. Easy with cups because you just sort of split them up. Take away the number the number you first thought of, which is that. That's n there, isn't it? So I take that away. What am I left with? I'm left with 3. So it's a really nice, it has its limitations, but it's a really nice way of representing what's going on there. You don't do that first off, of course. You invite students to try and do that themselves and see if they can represent what's going on. So really what I'm doing there is just showing you some ways that you can develop thinking about number properties under the operations with students without it becoming incredibly boring. And they do like this kind of challenge and something mysterious going on. And there are lots of examples of those, and we hope. Okay, so when I think about algebraic thinking, and that's the term that's used in the research mainly around what we do at primary levels, is I think about these things. We're developing the kind of thinking that we want students to have that supports them to make sense of, if you like, formal algebra when they start getting into symbols. And so I'm always looking for pattern and structure. Pattern is consistency. I'm looking for structure and trying to figure out how's this pattern organized, which is a way it was leading to, can I explain why it's happening? So structure is about organization. I'm always looking for things that change and things that stay the same. So things that change in a pattern are variables because they vary. And some things don't change, and they're the constants in a pattern. And it's really important to be able to distinguish those. Thinking about without closure is the idea that you can think of you can think of any number and work with it without having to close it off. What's a good example of that? You go to the shoe store, they've got or any store at the moment actually, and they've got a special going on. If you buy 2 pairs, then you get the second pair half price. And if they're the same price, these pairs, what discount do you get? If you're thinking with lack of closure, so you're thinking not having to close that off, you don't care what the price of the shoes are. It's really interesting to watch people work on that. Some people give the shoes a value, and some people go, hang on a minute, they're kind of visualizing any number and doubling that and then chopping that in half and figuring out what the discount is without giving the value of the shoes. So that's what we would call thinking without closure. It's Collis's idea from way back in 1994, and it's really important to algebraic thinking. And generalization, as we've said, is is the recognition that something is consistently happening here, and we go beyond generalization and try and explain, come up with justification about why it's happening. So generalization and pattern and structure are closely related. John Mason would say if you have a maths lesson without generalization, it's not really a maths lesson. That might be going a little far, but and we shouldn't forget that algebra is actually a language for expressing relationships and for deriving new meanings. So we don't just find out about a particular pattern. The way we express things algebraically allows us to find new results. And we have some representations we can use. Words are pretty important. Equations, we tend to think of algebra as just being about equations, but it's not. Graphs and diagrams are very, very important, particularly diagrams when you're dealing with young students. Okay, so let's pursue this pattern, the yellow box, if you like, and we'll touch on computational thinking a little bit in the process, I think. Just be careful of time. Okay, so here's some students. They're from just out of Melbourne, and we've got lots of different things for them to make patterns with, and you can see some roosters and cows or something going on there. So that's what we tend to do. There are only 5, I think, from memory. And you notice how we've set them up on a board like this. So we've actually explicitly trying to get a relationship going on between the ordinal numbers and what object is there. And they started doing all sorts of interesting things with their patterns. Some of them had, well, they're all facing the same way. We had students having a couple of variables going on in their pattern where they change the objects in sequence and change the position, whether they're facing up or facing down and that sort of thing. So you give students the license to do that and they come up with really nice pattern examples. So that's what we tend to do at junior primary school. And of course, we're inviting them, can you copy that pattern? Just make it. And can you think about what the next one is? And then it gets more complicated as we predict ahead about what the 10th one's going to be or whatever. Now, let's push ahead to something that I put out in the Learner First website, which is quite popular with teachers nowadays, which is nice because it's a nice avenue for sharing things. So here I've got a sequential pattern, but I've made it more difficult because I've left a couple of shapes, figures, or whatever you want to call them, out of the pattern. And this is what Rob Prophet White would call a move and prove. And it could just be an activity, couldn't it? But a move and prove invites the students to opt for either A, B, C, or D, and they go to the location in the room that matches their choice. So if we were doing this with a class, and he sees it as a kind of diagnostic tool, which is really nice, they would look at trying to work out which of the options A, B, C, or D would fit in that space, the 2 spaces, to make that pattern consistent. So it's quite complicated, this pattern. So have a think about it yourself and make a decision. And then we'll have a little play with how computational thinking might help us here. And one of the things we might want to do, if you like, in the first step in our algorithm is to say, well, kind of what are the variables here? So what have we got? We've got color. Okay. What else have we got? Well, does the shape itself change? No, but its position changes. So how could we describe its position? Oh, that's interesting. So what could we say about the position of the object? And there might be 2 things there. We might be saying, we've kind of got this idea, is it right way up as it starts, or is it upside down? And the whole idea of reflection as well, haven't we? we've got this notion that it's facing that way, like it is at the start, or it's facing that way. And all of those variables we could kind of look at as well, I mean, trying to think about them all at the same time is really hard. So maybe we would want to sort of have an algorithm that kind of allows us to look at those variables kind of separately. So let's see. So this is when we start to define the variables and start playing with them. So we'll just give these terms some numbers. And we'll start going, okay, well, what's going on with color? Well, let's have a look. If you, pardon me using R for red, then we've got red, black, black. And then the fourth one is red again. And then we've got black, black. Okay, and presumably we could keep on going here, couldn't we? But we're starting to see in that variable what's going on. So what if we move to the position? So we have, let's imagine we have them facing up. And then we seem to have two facing down, relative to where we started anyway, and so forth, right? And we could think about the position of them. So this first one's sort of the head of the frond is facing that way. And all that seems to kind of go on again, doesn't it? So what we're doing is developing an algorithm which would allow us to predict what we need to have here. So this is the first one, second one, third one, fourth one, fifth one. So what's the sixth one has to look like? Well, it should be that way, and it should be that way. So what should we have? We should have a black fern frond facing up for the sixth one, and it should be facing to the right. And that kind of narrows the field a wee bit, doesn't it? So what you've got there is an algorithm is really an established set of procedures. And I don't think many students are ever exposed to the idea that you can basically turn analyzing a pattern into a step-by-step procedure, starting with the variables, what are they, using the ordinal numbers and actually mapping it out like this in a kind of table. So that would be an example of where computational thinking interacts with sequential pattern. Now, I've got 5 minutes of all the things, lots of things I could do with you. One would be getting the mouse to work. That would be kind of good. And there's another one too. You'll no doubt get the PowerPoint made available to you. That's another one we put on the website. Slight different pattern, but same idea. This time it's thinking ahead. Now, I just want to move beyond that to growing patterns. I think one of my favorites at the moment is this lovely parachutist's pattern. And I was looking for something for my students in Melbourne one day, and I thought, this is kind of cute. The formations that parachutists form, and that's what we mean by a growing pattern. We need to be a bit careful because growing patterns don't always grow. They can actually shrink. There's a lovely one we made up on NZ Maths where some bug is eating into something. So growing patterns also get smaller. So that's a growing pattern. Now, what are we interested in here? We're interested in the stage of the formation and how many parachutists are. So that's the relationship we'd be exploring if we were looking at that pattern. But I just want to show you my latest one. This is Matisse's horses. If you're an art fan, you'll know who Matisse is. But I just got 5 minutes to show you what this approach might look like. Okay. Now, you notice I don't start with this growing. I don't start with one horse and then have 2 horses and 3 horses. I'm throwing you at the 5th term, really, if you're thinking about the number of horses. Now, first job is to find a way to count the number of horses. So away you go. Where can we review? That's the best we can do. So what we're wanting students to do here is to structure the way that they count. And they see all sorts of different things, different students see different things. We are in the parlance of the research into growth patterns, we're asking them to behave figuratively, which means they're attending to the spatial stuff. And we are encouraging what they call abductive reasoning. We're saying basically, can you structure one example rather than give people a sequence, which is fine. That encourages a different kind of thinking, inductive thinking. But here we're saying, can you structure one example? Because in the structure of one example, we might have the clue to all of the pattern. And let's put some examples. So let's see if you can get inside Julie's head, as this is the way that she counts the number of squares. So she's starting on the right-hand horse, and she's adding on horses. And those add-ons are all the same size. So that gives her a way of counting the number of squares. Then we might say, well, how might Julie write down the calculation that she performs? And she wrote 11 for the first horse and then 4 lots of 8, because she's a very efficient multiplicative thinker, and she comes up with 43. The challenge there, and I'm going very fast, too fast, would be, well, what would she do with 11 horses? And there's a little picture there to help them. 100 horses is getting tough if you want to draw it, so you're going to have to go beyond drawing. So what we're doing there is we're taking a specific example to start, pushing that out, and seeing if that same structure applies to more complex examples. And what you kind of get, if you can imagine, if we take Julie's example, and I know you're going to tell me, Marla, to be quiet in a minute, but when the kids start writing the equations for the way Julie thinks, then we get generalization through the equations. That's always there, the first horse. But if she's thinking about 11 horses, then she does this. And if she's thinking about 100 horses, she does this. And then you can get the students thinking about the things that are changing and the things that are staying the same. There's a bunch of things that are staying the same. Well, the 11's always staying the same. The plus sign's staying the same. That's staying the same. What's changing? This value here. How do we describe this value here? So that's just a snippet of what we could do, what we can do with growth patterns. And I will include with the PowerPoint some other examples, and not just Julie, of other ways of seeing the pattern. And that's kind of all we've got time for, really, I think.